Hey there, awesome physics students. Let's talk about conductors and electric fields. You probably remember that conductors had a special property that said that charges are allowed to move freely inside of a conductor. Because of that special property, they have some special configurations with electric fields. So let's see what those are. First of all, let's think about the possible electric field direction on the surface of a conductor. So here's a flat conductive surface, just to keep it simple. And let's think of the electric field at the surface can be at some angle here to the surface. We can break this electric field down into a component that is parallel to the surface and a component that is perpendicular to the surface. Let's look at this component that's parallel to the surface. If there's any free charges, and of course there are free charges all throughout the conductor, on the surface they will feel a force in the direction of the electric field. So positive charges will then feel a force in this direction and they will move. If I get too many of them moving in this direction, and I will get a buildup of positive electric charge here, negative electric charge here, that will create its own electric field that opposes the one at the surface. And eventually these charges will move around until the electric field is no longer parallel to the surface. In other words, the electric field can only be perpendicular to the surface of a conductor because any parallel components will move the charges around until there is no more parallel component. All right? And this is true even if it's a curved surface. So the electric field has to be perpendicular to the surface. Or if it's some weird, wacky, undulating surface, the electric field has to be perpendicular to that surface at all points. Okay? Let's think about another property of electric fields. Let's imagine you have some blob of conductor, and you put charges on it, and you spread these charges, these positive charges throughout. And what are they going to do? Well, of course, we know that we've already talked about this. The charges are going to try and get away from each other as much as possible. So the way to do that is for them to go to the surface, and that allows them to get the maximum distance away from each other. Okay, so all of those charges will be on the surface. Now, if there's still some positive and negative charges in the center here, right? The whole thing is just positive and negative charges, but overall there's equal amounts. Imagine if there's an electric field inside here. Let's say this electric field points up like that. Then the free positive charges inside the conductor will then feel a force up here, and they will begin to accumulate up there. And likewise, the negative charges will begin to accumulate down here. This charge configuration will then create its own electric field that opposes the other electric field that I just imagined that might exist there. And what you'll get is eventually this will continue to happen until these two electric fields add up to zero. And so inside of a conductor, the electric field must be zero. Another way to say this is that if the electric field is not zero, the charges will move until they are in a configuration that makes the electric field zero. Okay? So the electric field must be perpendicular to the surface, and the electric field must be zero inside. Let's look at one more useful and interesting component here of electric fields. Imagine I have a conductive surface like a fork or a knife, and I put it in the microwave or something like that. And there's some outside electric field. Well, because of this, the electric field must be perpendicular to the surface. So if I have an electric field like this coming in, it's got to be perpendicular to the surface here. And here, too, it's got to be perpendicular to the surface. And I'm just drawing it like this. And you'll see that what you get is you get if you look at where the field lines are, the field lines are farther apart on these straighter sections. And at the tip, you get a convergence of electric field. And that convergence is simply due to the fact that this is pointed here. And so because there's a convergence here, when the lines are closer together, that means the electric field is bigger. So the electric field is very big here. And what that means is there must be a lot of charges. They got to be negative charges in this scenario. there's a lot of charges built up in this at the tip here. And what that as a practical matter, what that means is that the electric field is very big around sharp edges, but for a practical matter for your microwave, if you put a fork on the microwave, the electric field on the tines of the fork are going to be big, and it could cause it'll cause a buildup of charges on the tines, and you might even see some sparks jumping across the tines of the fork. And that's why you're not really supposed to put one reason you're not really supposed to put metal in the microwave is because you get this spark, and that can cause some feedback that can ultimately cause some damage to your electronics in the microwave. You can put, metal is okay actually in the microwave. You'll see some microwaves, many microwaves have racks in there, and the racks are made of metal. So it's not all metal that's banned. It's just certain configurations are not helpful. Incidentally, you can make use of this on houses. What they'll do is they'll put a rod at the top, and this is a lightning rod. And what happens is, because this is sharp and pointed, when the clouds pass over and there's a big electric field from a lightning storm, the electric field lines will build up here, and this will actually bleed charge off from the cloud, and you'll get charges sort of traveling down here, and it'll bleed enough charge off so that the electric field or the clouds don't have this huge buildup of charge that could cause lightning. And so actually if enough houses have this, then it can actually prevent lightning strikes in a city or something like that. But if lightning does strike, then hopefully it will come down here. You have a big thick wire that will take it into the ground, which is the ultimate reservoir for electric charges. All right. So here are some of the rules of electric charges electric fields with conductors. They have to be perpendicular to the surface. The electric field inside the conductor is 0, and wherever there's sharp edges, you get a very large electric field.